All right, well, in this problem, we are given information about two different people and their velocities. One in terms of a table giving selected velocities at different points in time, and the other person an algebraic function of velocity as a function of time. And we're asked to reason using the information about velocity. We're asked to reason about a number of things. We need to find accelerations and distances, as well as average values of accelerations and velocities. And so the key here will be the concepts that we've listed on the right in blue, how we connect velocity to other related qualities. We're going to need average rate of change of a function. We'll need to recognize total distance traveled. We'll need to know how to calculate the average value of a function. And all the while, we need to keep in mind the relationship between position, velocity, and acceleration. So let's start with part A. And here we're asked to estimate v prime of 16. Well, the thing that we notice right off the bat, v prime of 16 for Joanna, whose velocities are represented in this table, is that we don't have any information about what's happening at t equals 16. And so we're trying to find the average rate of change of a function at 16. We have the values of that function both before and after 16. And so we're going to say that the best way to do that is, because 16 is midway between 12 and 20, we're going to use the average rate of change of the velocity over that interval. Okay, so we're going to estimate v prime 16, the acceleration at t equals 16, as the average rate of change of the velocity over an interval that includes t equals 16. It's important for you as a student to understand that this is only an estimate. There is no theorem here involved. We're not using, for example, the mean value theorem for derivatives, but simply grabbing the information that's available and trying to come up with a reasonable estimate. And so what we're going to do is say that the average rate of change of v is v20 minus v12 over 20 minus 12. And that's going to be 240 minus 200 over 8, or 40 over 8, or 5. Now, what are our units? Well, the velocity units themselves are meters per minute. And so the rate of change would be meters per minute squared. So we'll write it that way. Meters per minute squared. Now in part B, we're asked to interpret the meaning in the context of this problem of 0 to 40 v of t, actually the absolute value of v of t dd. Okay? And it's important that we recognize pretty much immediately that the absolute value of v of t, when we integrate that, that gives us the total distance that some object traveled. because it records the change in position both as the object moves with positive velocity as well as the change in position as it moves with negative velocity, and adds together those net positive changes. So we'll just describe that. That's the total distance traveled by Joanna from t equals 0 to t equals 40. And what will the units be here? Well, again, let's keep this relationship in mind. We were working with meters per second, but we're integrating with respect to seconds, with respect to time. And so our units are meters. Okay? And we'll use the Wright-Riemann sum approximation. Okay, so this total is approximately equal to Wright-Riemann sum. That means that we're going to work with this interval using this height. We'll work with this interval using this height, this interval using this height, remembering, of course, that it's the absolute value of that height that we'll be working with, and then this interval using this height. So, in other words, it's going to be 200 times a distance of 12 plus a height of 240 times a distance of 8 plus a height of, again, positive 220 times a distance of 4 plus a height of 150 times a distance of 16. Again, where I'm saying distance, I'm just talking about movement along the canonical x-axis, so those distances are seconds. Okay, and it's that many meters that we're traveling. Again, I'm leaving that in unsummed form simply because that's not required to get credit here, and why take the time necessary to add that and risk the chance of a mistake in the addition. So now we'll go on to part C. Okay, so now we're working with Bob and his velocity given as capital B of t. Okay, we have to find Bob's acceleration at a specific time, t equals 5, and acceleration is going to be the derivative with respect to time of v of t. So a of 5 equals dB dt at t equals 5. dB dt at t equals 5 equals, we have b stated, so we're going to take the derivative of that with respect to time. That's 3t squared minus 12t, and that has to be evaluated at t equals 5. So we have, continuing down here, 3 times 5 squared minus 12 times 5, or 75 minus 60, or 15, with units of acceleration units, which are meters here per minute squared. Finally, we need to find Bob's average velocity. Okay, well, Before we were finding the average rate of change of the velocity. Now we're finding the average velocity, and so we use this construction, this formula over here for the average value of a function over an interval. And so we'll write that as the integral from 0 to 10 of b of t dt, and then we'll divide by the interval in question, which is 10. Okay, and so that comes down here, and we get 1/10 of, let's integrate that term by term. The integral of t cubed is t to the 4th over 4 minus 6t cubed over 3 and then plus 300t, all evaluated from 0 to 10. Now the value at 0 is manifestly going to be equal to 0. And so, just going to make sure it's clear that we're separating this. Let's just bring this down to the next line. We've got 1/10 of 10 to the 4th over 4 minus 2 times 10 to the 3rd plus 300 times 10. And the units are meters per minute. Because it's, again, just a velocity that we're estimating.